Check. hear me? Eugene?
Yes.
Oh, okay.
I think you should be muted though.
Okay. You mean until I start speaking in 8 minutes? Is that what you mean?
Yes.
It's not working.
Welcome everyone to Access New Jersey's March session of Meet the Cobot. Today, we will demo live a Universal Robots collaborative robot. But first, let me introduce the presenters. My name is Cynthia Cradgell. I'm an account manager for Access New Jersey, and my focus is working with clients who are interested in learning more about robots, identifying where they may fit, helping to specify a solution, and then finally coming up with an implementation plan. My colleague, Karthik Ranjajaram, is a master's in mechatronics from NYU, and together we work with our clients to make sure their projects materialize successfully. He has a degree in mechatronics and a background in programming. So after we finish our introductions, Karthik will take over and demonstrate the robot live to you. But first, let me point out that we encourage you at any time to put questions into the chat. And at the end of our session, we'll have an open discussion to go over any questions and thoughts that you bring forward in the chat. The presentation will be archived on both YouTube and Facebook. And many customers, I have to say, are really interested in collaborative robots. For one reason is that they can be working side by side with humans. So unlike traditional industrial robots where you'd have to specify something, you'd have to put it behind a cage, and then if something changed, you'd have to sort of start over again. In the case of the collaborative robots, we find that customers sometimes bring it in for a project, and when that project is completed, the customers redeploy it to another use. Access New Jersey is a high-tech industrial distributor, and we're a privately held company. We're owned by PowerFlow Technologies, and we have over 300 employees, many of whom are engineers, and we have a wide depth of application expertise to help customers. So enough with the introduction. I'd like to turn it over to Karthik, who's going to take it over and show you how to program the Universal Robot.
Thank you, Cynthia. Hello, everyone. Today we're going to see about a demo on how to use Universal Robots, how to program, and also its technical specifications, features, and how to set up. And Universal Robot comes with, of course, the robot, a controller, and a teach menu to program. Universal Robot has two generations, the older generation called CB series and the latest generation called E series. Today we're going to talk about and see how to program E series. The one major factor on the upgrade on E series is that the force torque sensor is built into the robot, which can add like a sense of touch, feel and touch while programming or while using the robot. And there has been more features like better post repeatability and faster bus communications, and also like more I/O ports on the controller side. Under E series, there are 4 models based on different sizes. One is UR3E, 5E, 10E, and 16E. The numbers 3, 5, 10, and 16 represents the payload in kilograms. As the size of the robot increases, the reach also increases, except for 16, which lies somewhere closer to UR5. Today, we're going to see about UR3E and how to program. Regardless of the size of the robot, the controller is going to be the same, meaning it provides the same safety features, the same number of I/O ports, regardless of the size. And each robot has 6 degrees of freedom with 6 rotating joints. One is the base, elbow, shoulder, elbow, wrist 1, wrist 2, and wrist 3. The reason for Universal Robots being collaborative is because it offers 17 various safety functions, including going to a protecting stop when upon collision, and creating safety planes for the work environment based on how risky the environment is, and so on. And we'll be looking at one of those features during the demo. And the controller offers 16 digital input outputs for connecting various devices, and also offers 2 analog input output controls with 24 volts, where you can connect various analog devices to. And in addition to that, there has been 4 digital inputs for controlling the conveyor tracking. This is over like 20 digital inputs to control various devices. And on the tool side, there are 2 digital input output for connecting grippers and vision systems and so on. And also offers 2 analog input output devices, which provides 12 to 24 volts. And UR also supports various communication protocol like TCP/IP, Ethernet socket, Modbus TCP, and Profinet, and so on. And the robot, the whole build itself is so modular that the joints are easily replaceable and it can be connected and disconnected very easily. Now, enough of the technical specification. Now let's look into how to program the robot and how to set it. The teach pendant has the software called Polyscope, and you can see the display on your left side. Uh, it shows all the user interface and how to like communicate and how to program the robot. The initialization screen shows what the status of the robot is, whether the robot has been powered, booted, and is the robot is ready to use. With all the green checks, even including the brakes on the robot. So once with all these green checks, we are ready to go. Let's click exit and look into the user interface. The Polyscope offers a toolbar which provides each of the menu with a drop-down, and the drop-down consumes the entire space of the teach pendant or the user interface, giving you access to program and control and set up the robot. The toolbar has run, program, installation, move, input, output, and locks. So clicking on those buttons would give a drop-down for each of those uh, menu items. The run command allows you to load the program based on what set of programs have been programmed previously, and you can load and run immediately. And the program tab allows you to create programs, and the whole interface is divided into 3 sections. On the left is the node list, which generates or creates the node functions. And in the center is the program tree, which connects all those nodes and executes sequentially. And on the bottom, you can see you have like the same features as cut, copy, paste, moving the nodes up and down, or even like delete, or you can even comment it out called as suppress. And on the end of the section is divided into 3 parts. One is command, graphics, and variables. Command is the information where it shows the parameters for the selected nodes, and based on different nodes has different parameters, it shows up accordingly. And the graphics shows uh, the way the robot is in the environment. It shows all the joint positions with a 3D model, and you can like swing around back and forth and see how it is positioned. And the variables tab has all the informations of the program variables while executed. Right now there are no programs, so no variables are being shown. Once we write a program and execute, we will see what the variables tab has. And the third tab is the installation, where you set up all the basic information of what the Universal Robots installation is. Like it could be what kind of devices are connected to it, and to the controller, what set of devices and what kind of safety planes are connected to it or defined to it. And we'll look into this very detailed shortly. And Move tab represents the way the robot is controlled in 3D space. And Universal Robots allows to control in various forms. One is the free drive button called free drive process, which has a free drive button on the teach pendant. Pressing that would release the brakes of the joints on the robot, but it doesn't collapse, meaning like it holds its positions where it is, and I can swing where I want to. You need to be careful while applying the force, meaning like it has to be at a certain pressure or force. If it's more beyond that, it would like go to a protective stop. Let's look into the other aspect where the robot can be controlled through the view position or the feature position, where you can see the robot's graphical interface and in the 3D model, 3D space, and you can move the robot up and down, right, left with the TCP orientation. And the other way of controlling the robot or move the robot or jog the robot is using the tool position, meaning where the tool is connected to it, you can move based on the XYZ and rotation of that particular tool position. And the fourth set is the controlling each of the joints individually. Let's power the robot and let's look into that. So as you can see, the free drive is a process where you can control the robot in its 3D space with all its joint angles. And the joint position is where you can control the robot at each of its joint. As I told you before, this is the base, shoulder, elbow, wrist 1, wrist 2, and wrist 3 here. So you can individually control those particular joints in the way you want it. And you can also control the robot with its DCP pose. As you can see, it can be controlled up and down, right, left, where you want to go. And the fifth tab is the IO controller, IO tab, which defines all the informations or the devices connected on the controller side. It shows up all these devices based on how you set it up. And the sixth tab is the log, where it logs in all the informations. As you saw before, we did see some safety violations. So it gets logged every time there is a violation. And let's dive into programming the robot now. In the program tab, the nodes are categorized into 4 sections: basic, advanced, template, and UR caps. We'll look into each of these one after the other. Basic has all the basic functionalities for making the robot move or command in such a way that it can be set up easily. Advanced allows you to like control the robot with more condition based on like if else statements, or based on a loop, or if you have like a thread program to run parallel with the robot, you can do multi-threading in UR. And if there is a need for including a complex programs, you can use UR script. And for more information, you can check Universal Robots website for UR scripting. The template is a another feature added within the UR, which allows you to have a predefined template for certain processes like palletizing, for example. You need to define certain waypoints and the positions, and the robot would compute and calculate all its motion and the calculations of how the grids are placed in a pallet, and you can set it up very easily. And UR caps is a entirely different set of nodes. The first 3 nodes, what we spoke about, the basic, advanced, and template, is more of an inbuilt into the robot. The UR caps is based on the third-party companies who define these nodes based on the devices connected to the robot. Based on the set of grippers, it could be, or it can be like safety devices connected to the controller or a vision system. So each of these nodes are generated by those softwares, and you can use those nodes along with the predetermined or pre-built nodes. Now let's begin to start a program. A simple pick and place would require an approach position, a pick position, and a drop off position, and an exit position. So let's create all those, and as we go, we can look into what these features are. Now, generating a move function, the Universal Robots offers 3 different motions for controlling the robot. We'll look into each of those 3. There are 3 motions, which is move J, move L, and move P. Move L, in the sense, it's a linear move, meaning it can move in X, Y, and Z in the same direction, like a straight line. That's the shortest path between the 2 waypoints in a same linear motion. Move J is a joint move, meaning it would find any shortest move between 2 different points in a different 3D space, and it would find a shortest path, but it wouldn't restrict any of the joint angles, meaning it would find a shortest path, but in a smoother way. And move P is a process move where you can define very specific motions, like in examples like gluing or welding, where it has to move in a certain specific angle with a consistent speed and acceleration. That's when you can set up with move P. Now let's define a move J and create a waypoint. And I'll be using the free drive to position the robot. And let's set this as the home position. And now let's create another waypoint where we need to pick this part, and let's position the robot right on top of it. And you can see here there is an align button which aligns the robots in its Z position so that it's parallel to the part. And let's define the pick position. And Let's create a move L where it has to go straight to pick the part. So this is the waypoint right here. And let's update the waypoint to right before the part. So from the home position, it would come over to the approach position and move straight in the linear motion to pick the part. And now comes the part where we can activate or actuate the gripper. And here's where I can show you or demonstrate on the how easy the UR caps are. UR caps generates the nodes for actuating or controlling the gripper. And just before the start of the program, let's say activate the gripper, it activates. And let's say the gripper has to be in a move in the open position before picking the part, and then it would start the process. And this is where the robot would pick. And let's update this waypoint all the way down. And now that the part is ready to be picked, we can have the gripper actuate to close the gripper so that it can pick. And now that it's closed and it's steady, what we could do is we can create another waypoint right after the gripper close to make it like an exit position from the pick pose. And now that it has picked from here, we need to create a move J process where it can like drop off to a point. So let's create a move J, and let's say it needs to clear some space over here. Or we can even define right before it drops off. And what we need to do here is to create a move L to move the robot linearly. Right here. And set this waypoint right on top of this drop position. So now that it's here in this position, we need to open the gripper to drop off the part. So what we're going to do is create the gripper position to open. And now that it's dropped the part, we need to make an exit position, or it would go over to the start point with the move J process. So we had to make sure we need to include another waypoint as an exit waypoint so that it's clear off of the drop point and it should be good to go. Let's test it out. And it should be able to do the whole running process and it should execute. This is a simple pick and place applications where you can see how quick and easy it is to like connect each of these nodes and how to like program the robot. As you can see here, each of these nodes are executed sequentially, meaning it executes one node completely and then goes over to the next node. And once this whole thing is done, this would repeat the whole process. So if this is something which you are not looking for, by tapping or clicking on the robot program, you have the options on the bottom side where it says program loops forever, meaning this whole node would repeat forever until it is stopped or it goes into a position where it has detected or collided into something and it would go to a protective stop. So let's look into that feature and see how it works. Now that the robot is picking the part, and if it's colliding to something, someone or something, it would give a protective stop saying it has collided and it violated the joint angle with a specific force or pressure, and it says like check the collision joint, and it gets logged into the logger on the controller. So once you click enable and you clear the collision off of the place, or if it collided into someone and you're clear of the environment, and if you click continue, it would continue from the point where it stopped, meaning you don't have to restart the whole process. You don't have to remove the part out of the gripper and reactivate anything. It would continue where it has dropped. So now that we have seen the features of how to program the robot, I'll show you what is the installation process. When setting up any robot or any devices or connecting any kind of a gripper into the tool flange, there are three things or three important points which you need to make sure it is updated on the UR. One is the tool center point. Tool center point or TCP defines for the robot where the part is being picked from. So if there is any attached custom tool or an extended tool tool device connected to it, so you need to define where the part is being picked so that the robot would compute the inverse kinematics for each of the joints based off of that tool point. So right now, if the tool is not connected, the tool center point is 000 for the robot, which means it would be on the tool side. It's not here. So this would make two problems. One, it would compute entirely wrong based off of the part where it is being picked, and two, if the TCP is not updated, this would create a problem to the joints as well. So you need to make sure the TCP is updated. And the second important point is the payload. So as we are seeing here, which is UR3, it has a 3 kilogram payload capacity, which is excluding the tool. So any payload you're attaching to it is the payload which you need to update on the installation. Based on the payload would be the total of the total weight of the tool plus the weight of the object you are picking. So if the tool is like 1 kilograms and the part you are picking is like 500 kilograms, you need to update the payload as 1 kilogram and then active payload while it is being picked as 500 grams. So it would be the active payload would be 1.5 kilograms and the payload would be 1 kilograms. And another third important aspect is the center of gravity. So center of gravity is where the payload or the tool and the object being attached to the robot is based off of how the part is being balanced. So if the center of gravity is not updated, meaning the joint angles are computed based off of a zero center of gravity, it would apply wrong force and wrong joint angles, and this would break the joints on a long term. So for all these three important tasks, the Polyscope provides you to create like a simple way with a tool wizard where you can set up the positions, the TCP, payload, and the center of gravity using these wizards. So clicking on the wizard, it's a very simple tool where you had to define a very specific point and move the robot based off where you want to pick the part and set up four different points at four different angles at the same point, and the robot would compute the TCP, payload, and the center of gravity by itself. And another important information on the installation is your safety functions or safety configurations. So under the safety parameters, you need to define how the application is going to be. Is it going to run at a faster speed? If it is beyond a certain limit, you need to like have safety planes or safety devices set into it. Or you can use the UR's internal features called say creating a safety plane, where beyond that limit, the robot would uh, maybe reduce its speed or go to a stop if it exceeds that particular plane. So you can restrict all of the joints, or you can restrict based off of the elbow if it's reaching beyond that point. So we'll look into that aspect right now. As you can see here under safety planes, you can create multiple planes where you can define within that limit or beyond that limit, the robot has to either like go to a stop, or you can go to a reduced speed. So here you can see there is a plane right after the robot where I'm standing, and there's a plane right here created between the robot and myself. So this can be controlled, as you can see here. Let's unlock, and this should it should shut down the robot, and it would allow you to create the safety planes. This is in order to protect the robot and the environment where the robot is working. So if there is a safety configuration change, the robot would shut off. You need to make the changes and save the safety parameters and boot the robot back. And now that we have set up the plane 1, let's create a plane 1 right here, or let's create for the plane 2 and click apply. This is the plane where it is right now. Let's click apply and restart. This would save all the safety parameters, and it would give us the information as to what the changes are, the normal speed and the reduced speed. And once you click confirm and everything is set, and power the robot. And these safety features can be created under features, and you have point, line, and plane. Creating a plane would allow you to like move the plane in XYZ and rotate in XYZ. And based on how the applications are, you can move these planes in the 3D space, and this would set up a safety plane. And going back to the plane here, now that it's been set to reduced mode, it's good to go. So now if I move the robot beyond its point, like towards me, that's where the robot would go to a protective stop. Let's power. So as you can see on the display here, if I move, I'm restricting the elbow position. So if I move beyond its point, this plane is where it goes for a violation. It says the safety system has been set to a lower speed and I'm moving the robot at a faster speed. So we can see how it works in a application where we are like setting up right now. And with the current program, let's modify the drop-off point on the other side so we can see how the robot would change its speed. And this is where the drop-off point was. So let's change be here, and let's move this waypoint to over here. And waypoint 7 goes all the way down to drop off. And that should be it. Okay, let's test it out. Hmm. So gripper, where was this? Here. Let's set waypoint 5 here, and this one should be all the way down. Okay. So now you can see on the graphics how the speed would change when it comes towards me. Since the plane is beyond the elbow, so let's just for test, let's update the waypoint of this one. Uh, let's say this has to be beyond its limit, and it should pick. So now if you see the robot beyond its safety plane would go in a reduced speed. As you can see, it reduced its speed based off of the normal and reduced mode. And looking at the template, we can look further on how the palletizing program would work. I would just show you an idea or a, a way of like how to create the program. So let's delete these waypoints. And in the palette program, you can define based on how your palette design is or how the part you're picking up is. If is it line, grid, or irregular shapes. And if you have like a packing box where it is with separated with separators or sheets, you can define the thickness of that as well here. And in the layer, you can choose what kind of a pattern you are selecting. Right now, pattern is not selected. Let's say let's go by grid, and it would allow you to choose the points of that particular palette based on the points 1, 2, and 3, 4. And if you increase the rows, and it would increase the number of values of the parts as well. So you can define the four corners, and you can choose what kind of a layer you're selecting and what you need to do at each point, whether you need to do an approach, and if it has to like go to a machine where it has to do a machine tending application, or if the part has to be picked and placed into a conveyor based on the application. You can define all your tool functionality within this at each item. What it does is basically it would pick each part and process it based on at each item part what you define, and it would execute, and this would completely go through the palette, and it would define for all the separators. And so another part of the advanced nodes are like loops, a program, and creating assignments and if statements, and you can execute like script commands. So let's look at the loop where you can say with a part of the program you need to like loop this complete program all the time. Or if you want to like define a particular number of times, like if there is a part and it goes for like 6 times or 10 times, you can define that particular loop for 10 times. And if you want to like loop this particular program based on a device connected to the controller, saying if there is a sensor detecting the part, that's when you have to like start the loop or stop the loop. You can define based on that too. And any program within that particular loop node would get executed that many number of times. And assignment is a variable where you can create custom variables within the robot, and you can create like multiple variable names. These are user defined names, and you can create like x, y, z, or any meaningful names like variable 1, 2, or anything, and any values defined to it would get saved, and it can be used at any different point of the time within that particular program. If any variables is defined within the program, that's where it gets executed within that program. If you need to create like an installation variables, you can go to installation, and you can go to general, and this is where you can define installation variables, meaning any installation file which are created and any programs created within that installation file can use this variable for that particular installation file. And each of these programs can be saved through the save all, or which would save the program as well as the installation. Or if you have like a program which have been created before, you can open those programs. And if you have like a various installation files, you can open those as well. And you can create like new programs and create new functionalities. And the robot also allows you to like do two ways of control. One is the local mode, which is the teach pendant, where you can control through the teach pendant and create programs. And if you're looking for more robust or more advanced programming like Python or C++, the UR does allow you to do that through a remote control tab, where you can set it to remote control, and it would disable all the features on the teach pendant, and you can connect to a through a Ethernet socket, and you can program through Python or C++, and you can send your programs, more complex programs and features which you want to work with. You can do that as well. And those network connections can be checked in the burger icon, going to the settings, and under network you can set up the network IP addresses, and that would get connected to your host computer, right? Let's go back to the local mode. Are there any questions? Has there been any questions on the uh, Facebook, YouTube? Let us know if you have any questions, or if you want to like uh, look into any specific features. We can also use the E-series force torque sensor, which are built into the robot. We can use that for, as I said, it adds like a sense of feel and touch. So we can use this to find if the parts are there or not, and proceed based on what the information of the force torque sensor is. We can use that by using the nodes from the force torque sensor, which has a Copilot software built into the uh, teach pendant, and you can use those nodes particularly into the you can link those nodes into the program, and you can use those features right here. So what you can do is the place where it picks the part, you can define this waypoint all the way down, and you can use the open, you can use the cut copy paste right here. Let's put it right here. Let's close. Right here, there's a node called find surface, and you can use this to move the robot. And once this is found, what you can do is create a gripper open function, and this would go all the way down to pick the part, and close, and it should. So let's see how this function can be used. So the robot doesn't know where the part is, so it would search along the z axis. I have set the direction 2 with z plus, and once it detects there is a part, that's when it opens the gripper and picks the part. So rather than having like a vision system to make the more complex process, you can use the sense of touch from the force torque sensor to detect where the part is. The major advantage is that you don't need any complex systems to be connected to it, and you can use the force torque sensor to do the job, but it would reduce your cycle time. So it wouldn't be an effective way as the vision systems are. Vision systems provide you an access of giving the ability for the robot to like look before what it look before what it picks. So it knows where the items are before picking. But with the force torque sensor, it's more like it needs to search for the part, and that's when it processes. So if you have any questions, do let me know. All right, thank you everyone. If you have any questions or comments, do contact us. If you have any specific applications, we are there to help you out. Thank you.